All right, so we're ready to begin the morning session. Our first speaker, first of all, a reminder, in the schedule for today, the Robin Bloom Kahoot talk is actually going to happen on Thursday, and David Gossett is going to talk just before lunch. We get to start the morning session with Beni Yoshida, who's now at PI, and he's going to tell us about traversal logic gates and group cohomology. And we'll have a nice long coffee break afterwards. So hopefully we'll have a lot of questions and then a lot of discussion.
Okay, so yeah, thank you very much for an invitation. So I'm not sure. So it's this one. Okay. Anyway, so today I'm going to talk about transversal logical gate and group cohomology. And this is some very old problem, but yeah, let me talk about it. So this talk is based on the following two papers. The recent one talks about more generic framework, then the previous one talks about more concrete examples. So let's get started. So transversal logical gates, why is it important? Well, the underlying difficulty in quantum information science is, of course, the fact that quantum entanglement decays easily. Therefore, we need to protect qubits by using quantum error correcting code. The idea is you prepare a single qubit state and then run some encoding circuit. Then you encode information into many body entangled state. So that local errors do not destroy the encoded information. But here's a question. How do we perform logical gates? Well, at the level of single qubit, this is very easy because I just need to put some single qubit unitary to psi. But what about at the level of code word space? And this is very tricky question. And ideally, we would like to perform logical gates by transversal gates, which acts on each qubit individually like a tensor product form. Then if such transversal implementation is possible, then local errors do not propagate to other qubits. So it's fault tolerant. But if transversal operation is not possible, then local errors may propagate to other qubits. So then it's a mess. So given a quantum code, we would like to know what kind of gates can be implemented by transversal unitaries. Now let us look at a few examples. First, 7-qubit code. You see that, so these are the stabilizer generators. You see that it's invariant on the exchange of X and Z. So you can apply Hadamard gate everywhere on the lattice, on the code. Then this is a logical gate. Another example is the two-dimensional toric code. So these bracket-like and the vertex-like stabilizer generators, and then so you notice that this code has string-like X and Z logical operators. But if you carefully look at the Hamiltonian or stabilizer generators, then this code has only Pauli-like logical operators as a transversal logical gate, and no other gates. So in this sense, toric code has a really restricted set of transversally implementable logical gates. Another example is 15-qubit code. I'm not showing their generators, but this code has R3 or T gate. They are transversal, and this is good because it is a non-Clifford gate. Okay, so these are the well-known examples, but the question is, so at this moment, I guess no systematic approach to this problem is known. So the problem is, given the quantum error correcting code, well, how do we find transversal logical gates? Or conversely, how do we design a quantum error correcting code with useful transversal logical gates? And I guess this is a very long-standing problem. This is something you learn in, Nielsen Chan, but it doesn't mean that it's actually a very difficult problem. So I cannot attack the most generic problem. So in this talk, I will concentrate on certain class of quantum error correcting code, which is called topological quantum codes. Roughly speaking, it's a class of code where qubits or spins are sitting on a geometric manifold with metric, for example, lattices. And code generators are geometrically local. That's the definition of a topological quantum codes. So in this talk, I will try to provide a systematic procedure to attack these problems in the context of topological quantum error correcting codes. Okay, so in a few slides, I would like to state the main result of today's talk, but for this purpose, let me review some basic notions. So first, it's a result by Bravi and Koenig. So in 2012, they had a very important result. So instead of a transversal gate, they actually consider even larger class of gates, that is logical gates which can be implemented by finite depth quantum circuit. If it's finite depth, then it's still errors do not propagate too much, so it's okay. And then they also consider the local stabilizer code in this spatial dimension. And then under this problem setting, they were able to prove the following theorem, that is, in this spatial dimension, all you can do with low depth circuit is actually restricted to this level of the Clifford hierarchy. So the question is, what is the Clifford hierarchy? Well, Clifford hierarchy is just a hierarchy of sets of unitary transformation acting on n qubits. At the lowest level of the hierarchy, you have a set of Pauli operators, x, y, z, and their tensor products. And the second level is the so-called Clifford gate set. So C0, Hadamard, R2, and so on. So these Clifford gates transforms Pauli to Pauli. Okay. And third level gate P3 transforms Pauli to P2. And similarly, M gate, mth level gate transforms Pauli to M-1 level gate. So you can use this to define the Clifford hierarchy in a recursive way. And one observation is, in general, gates from the lower level of the hierarchy are usually easy to implement. But higher level gates are typically, they involve many qubits, or it involves like a small rotation around some axis. So it's more difficult to implement. So going back to their theorem, they say that in this spatial dimension, all you can do is limited to this level of the Clifford hierarchy. Okay, so I think given this result, naturally arising question is, of course, how do we construct a code which saturates this theorem? Also, we would like to generalize this result to even larger class of topological quantum code, like non-stabilizers. So let me introduce the model I'm going to work today. That is the quantum double model. Well, this model itself, originally proposed by Kitaev, was defined in 2 dimensions in the context of topological quantum computations. But you can easily generalize it to this spatial dimension. And namely, given a d-dimensional directed graph, and then with some finite group G, then you can define the quantum double model. Here you put qubits or spins on edges of the lattice and the graph, and then the qubits or spin are z-dimensional. And the Hamiltonian look a bit complicated, but it has this vertex term and bracket term. This vertex term just implements group multiplication, and then this operator measures the total sort of flux and try to project it into a no flux state. And the system has degeneracy, and so you can encode information into these degenerate ground states. So in this sense, this quantum double model is a topological quantum code. And if this group G is like Z2 and the several copies, then you get the stabilizer code. So for most of my talk, I will assume that this G is an abelian group. But actually, most of the argument actually can be generalized easily to non-abelian cases. But the reason is the Clifford hierarchy is well defined only for abelian group G. So that is the reason. Okay, so this is the model. Now, okay, so let me just state the main result, which seems a bit technical. But so the goal is I want to find the logical gates, transversal logical gate, a fault-tolerantly implementable logical gates in the quantum double model. And for this purpose, I first consider a d-cocycle function for group Z by studying the group cohomology. So I get some cocycle function. And then by using this cocycle function, actually I can construct a logical gate, which can be implemented by finite depth circuit. And that works for the d-dimensional quantum double model with symmetry group Z. Okay, so, but, so as a result, so now the question is what's the action of these logical gates, right? So if this cocycle function I used has a non-trivial sequence of slant products, so there is some object called, some map called slant product. And if this slant product is non-trivial, then this logical gate is actually a non-trivial this level gate. So it belongs to this level, but it's outside of d-1 level. So slant product is a map from n cocycle to n-1 cocycle. So starting from n cocycle, you can go to n-1, n-2, and so on. You can keep going. Then eventually you get 0 cocycle, which is U1 phase. And if this value is not equals to 1, then the corresponding logical gate is actually a non-trivial this level gate. So yeah, so the description seems a bit technical, but the procedure is very systematic. You just need to compute cocycle functions and slant product. And this part, mathematicians have done, I mean, for a long time ago. So I don't need to care about it. And then computing slant product is very easy. So it's pretty systematic. Okay, so that's the main result. But I actually found this result by solving completely different problem, which is actually more like a condensed matter theoretical problem instead of quantum information theory problem. So I would like to spend like several minutes to explain why this could be interesting to condensed matter theory cloud. But is there any questions so far? Yes.
Sure, I didn't miss. You said these are non-stabilizer codes.
Oh no, in some sense it is stabilizer code because I will be using abelian, so it's like a generalized stabilizer code.
Okay,
yeah.
Thank you for clarifying.
Okay, so right, so another motivation. So it's related to classification's gapped boundaries. So what is gapped boundary and why we need to care about it? Well, so we basically want to use topological quantum error correcting code to store information. But you might have heard that, well, if you have topologically ordered system, you need to put it on a torus or donuts or some geometry with some very weird topology. But realistic systems have boundaries. So the question is, can I still define topological quantum code even in the presence of boundaries? In particular, I would like the system to be still gapped. By gapped, I mean that there is a very big finite energy gap between code word space and excited error space. So this is a very practical, sounds like a practical question, but it has some fundamental flavor in it. So, so this problem was originally addressed by Bravi and Kitaev in 1998. So they found that the toric code has two types of boundaries. So they call it rough boundary and the smooth boundary. So this is the toric code lattice, so it's just square lattice. On smooth boundary, you just cut lattice smoothly, and the rough boundary, you cut it roughly. So that's the difference. So, but these two boundaries are very different. So remember that in the toric code, you can create electric charge anion and magnetic flux anions. There are two anions, but when you create anions, you need to create them as a pair, right? But so on the bulk, you need to create pair excitations, but on the boundary, actually, you can create, let's say in this smooth boundary, you can create magnetic flux as a single object without involving any others. So this is a single excitation. And similarly, on the rough boundary, you can create this electric charge as a single object without involving any others. So with these observations in mind, people started to think that maybe if we want to classify gapped boundaries, then given topological quantum code, maybe we just need to look at which anyons can pop out and diffuses into the boundary. So condensed matter physicists use this word condense to describe this physics. That is, if an anyon condenses into a wall, gapped boundary, this means that this anyon can be created or annihilated without involving any others. So the classification principle is you just need to find the level of anyons which condenses into the boundary. On rough boundary, electric charge condenses, and the smooth boundary, magnetic flux condenses. Okay, so now, but this is just a Z2 toric code, but how do we attack a most generic problem? Well, we had many evidences, but in 2013, or maybe 12, I don't know, Michael Levin proposed the following very interesting observation. He said that in 2 spatial dimensions, in topological order, levels of condensing anyons can be characterized by the so-called Lagrangian subgroup. But this is just a mathematical word to describe the following thing. So first, you just list all the set of anyons, like E or M or composite of E and M and so on. Then we look for the subgroup of this set. It's a subset, but it forms a group. And the property of this subgroup is the following. All the anyons in this group must braid trivially among each other. And this is very strong constraint because, as you know, anyons braid non-trivially among each other in general. So you only need a subset of anyons which braid trivially among each other. And then you want to find the maximal possible subset of such anyons. And roughly, this is the definition of Lagrangian subgroup. So he basically translated the problem of finding a gapped boundary into the problem of finding Lagrangian subgroup. And I'm not familiar with this field, but apparently topological phases can be well described by category theory, and this is a terminology from category theory. So he basically mapped this into a problem which mathematicians can understand, which is nice, so because they will solve it eventually. And but this idea, so I would like to check it for this toric code first. And now, in the toric code, you have a rough boundary where electric charge condenses. Of course, electric charge braid among themselves trivially. Similarly, M braid among themselves trivially. But the point is, you cannot define a gapped boundary where E and M both condenses, because E and M braid non-trivially among each other. So this is very consistent. That's why we have only 2 boundaries. And recently, Kitaev and Kong put this problem into the language of category theory, and then they constructed a gapped boundary for the Levin-Wen model and gave some sufficient and necessary condition for the presence of gapped domain wall and so on. So this problem, at least in 2 dimensions, we have a very good understanding at this moment. So I described about like gapped boundaries, but why do we need to care about it? Well, at least for me, it is very related to this logical gate problem. So fault-tolerant logical gates and gapped domain walls are closely related, and I even conjecture that actually there will be a one-to-one correspondence. But anyway, this is just my conjecture. So let me illustrate the idea by using the famous topological color code proposed by Bombing. So in this color code, you have qubits on vertices, on 3 colorable lattice. You have bracket term like XXXX, ZZZZ. So you have 2 terms per bracket. You see that this system has symmetry on the exchange of X and Z. So Hadamard is transversal. So you need to apply Hadamard everywhere on the lattice. Then you can implement some logical gates. But now by using this Hadamard gate, let me construct some gapped domain wall. So the idea is very simple. Instead of applying Hadamard everywhere on the system, I just apply it only on one side of the system, on the right-hand side. Then, so in this region, the Hamiltonian does not change because this is the symmetry of the Hamiltonian. So this part and this part, Hamiltonians remain unchanged, but only along this domain, you need to modify the Hamiltonian. But this basically defines the gapped domain wall because you have color code here, and some term here, which are changed by applying Hadamard gate. This domain wall is non-trivial because if you send E particle to this domain wall, then this E must become M must become E. So this is a non-trivial domain wall. And you can see that this argument basically works for any membrane-like logical operator because given a logical gate which can be applied by finite depth circuit, I can apply it only on the right-hand side. Then it will give me some gapped domain wall. So this is the reason why gapped boundary and logical gates are closely related to each other. Okay, so with these observations in mind, actually I can state my result in the condensed matter theoretical language in the following way. That is, we can construct a gapped boundary or gapped domain wall by using d-cocycle functions in the d-dimensional quantum double model. And some of you may know that so this problem has been solved for 2 dimensions by Bayesian Shaw and Wollam. For 2 dimensions by using 2 cocycle functions. So in this sense, our result generalizes their result. And okay, so that's like a generalization, but in higher dimension, actually, we start to see something very weird. So starting from 3 dimensions, actually, we can construct a gapped boundary where none of anionic excitations can condense. So in ordinary gapped boundary, either electric charge or magnetic flux can condense. But in this boundary, none of them can condense. But instead, they can condense only if they are accompanied by superposition of anionic excitations. So I will explain this later. But this is kind of puzzling at first to me. But at least this implies that we need to modify the notion of the Lagrangian subgroup in some way to have the complete classification 3D boundary or 4D boundary and so on. Okay, so now, just one comment. I was talking about gapped domain wall and gapped boundary and gapped domain wall are not exactly the same, but actually similar tools similar tool can be applied. So the reason is you can fold the lattice along this gapped domain wall. Then if you fold it, then you can view it as a gapped domain wall for 2 copies of the topological color code. So the same framework applies. So they are essentially the same. Okay, so here is like the kind of summary of the result. So the goal is we want to classify fault-tolerantly implementable logical gates. And that's something we can do by using group cohomology. But this is related to classification of gapped boundary. So it's like, yeah, we can get 2 results. So that's nice. Okay, so let me briefly explain the way how we construct logical gates. So from this part, it may be a bit technical, but I try to explain the idea and try to tell you the intuitions. So first step, we need to use the so-called gauging map. I'm going to explain the idea for G2 case. Gauging map is actually a well-known technique in condensed matter theory. And well, they say that this is a procedure of coupling your system to gauge field and blah, 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 which is not that well defined for we quantum information theorists. So I would like to formulate it as a duality map. It's bijective and isomorphic map between 2 Hilbert spaces. So you first need to think about 2 Hilbert spaces, H0 and H1. You have same graph, but in H0 you have qubits on vertices and qubits on edges. So now I want to define a map from H0 to H1, but they have very different sizes, so I want to cut down the sizes by looking at some subspaces. So as for H0, H0, I will concentrate on the subspace with global symmetry, which I mean, if I flip all the spins at once, then the wave function should remain invariant. So this H0 sim is such subspace. Similarly, I would like to define subspace of H1 with gauge symmetry. By gauge symmetry, I mean just the following. You always look at some closed loop, and then you say that this z, and this is satisfied. So when you think about closed loop, I'm allowed to talk about also non-contractible loop. So I need to think about all kinds of loops. Then I can define H1 sim. But with some calculations and speculations, you can actually see that this Hilbert space and this Hilbert space has exactly the same number of states, orthogonal states. So I can define some map between this H0 symmetry and H1 symmetry. It's a duality map. Now, so how do I construct such a duality map? Well, the idea is very easy. So A, B, C, D are some group element. In our case, it's 0 or 1. What I do is I just do the group multiplication. So A times B. So in the G2 case, it's just like 0 or 1 value. So it's like just summation under Z2. But in general, this is like A times B, C times B, and so on, and so on. So of course, this rule depends on the direction of the lattice. But you already see that if you measure the total flux, so you multiply the group element, then you get trivial element. So in this sense, you see that after this map, the wave function satisfies the gauge constraint. And so why do I need to do these stupid things? Or maybe it's actually a very nice thing. The reason is, let's take a trivial product state. Sorry, product state. And so this product state, so it's just symmetric over group element and everywhere. So this is just very boring, trivial product state. But now if you apply this gauging map, then you get a ground state of the quantum double model. This is very good because I got something very interesting from something very boring. So the reason is we already know that this gauge constraint is satisfied. So we already need to verify that this vertex constraints are satisfied. But to see this, you see that the applying X operator here is equivalent to applying X operator on these three edges. So since this state is invariant under this X, so you have this constraint. So that's why I have a ground state of a quantum double model. And this is nice because I can study complicated thing by using simple thing. Okay, the second step is group cohomology. And sorry, I think this slide does not make any sense if you don't know group cohomology. And if you know group cohomology, this doesn't help. But sorry, this one?
So maybe I just misunderstood. You map the state of 4 vertices to the state of 4 edges, right?
Yes, but you have some qubits of course here and here. So you are thinking about some graph.
Well, I was just thinking, yeah. So like vertex A takes part in other loops also. So how does it work to apply this to the entire system?
So suppose I have some graph, like big graph, and then I write down the wave function inside this space as a like in a computational basis, and then for each computational basis state, I can apply this map, and then so now the resulting state is a computational basis state on this lattice, right? Where qubits live on edges.
Okay.
Did it?
I guess what confuses me is the map looks like it's defined for each plaquette.
Oh, no. So for example, you have some qubits and then here, and then it has, let's say, E state,
yeah.
And then you have some qubits here, which is like D times E and everywhere.
Yeah. And does this give you a low depth way of preparing the ground state?
No, that's the point. So this is a non-local map because I'm creating a lagrangian entangled state.
Okay.
But in some sense, locality of operators are often preserved. So for example, in this case, X operator just expanded a little bit, and so. But it's not a finite depth circuit. Okay, so I want to use this, and then so next ingredient is the group cohomology, and the group cohomology is just some. It deals with some QuICS functions, and QuICS functions are U1 valued functions, so it's like complex phases, and with some complicated QuICS conditions, and these conditions are very important when we talk about SPT phases. But I'm just showing this definition to just remind you what I'm considering. Okay, so the reason why I want to talk about group cohomology is SPT, or symmetry protected topological wave functions, can be constructed by using the machinery of group cohomology. So to construct it, you just triangulate the system. So this is a triangulation, and then you always start from trivial product state, a symmetric trivial product state. Then you apply some encoding map U, or quantum circuit U, which is short-ranged, but it's not symmetry protected. Now, how you apply this operator is the following. If you find this triangle, then you apply this two QuICS function. That is, if your quantum state is in this G0, G1, G2 state, then you just add some phase. And you keep doing for each triangle, then you can construct actually a 2D. It's actually, I'm sorry, actually, it's actually, I needed to use 3 QuICS, but anyway, I'm sorry. So by using group QuICS, group cohomology, you can construct wave function with SPT phase. And then there is some typo here. I'm sorry. But the point is the state I get is actually symmetric. So if you flip the spins everywhere, then it remains invariant. So it belongs to this H0 symmetry space. Yes?
Is there a definite order you're choosing?
No, because this is a phase operator, so it's diagonal operator, so it commutes with each other. So you can apply it simultaneously. Okay. Yes.
It might be helpful if you, for the audience, could, going back to that slide.
Yep.
Provide the example just for the case where it's the toric code for one plaquette. What would this new 2 be?
So in order to get the toric code, we need to start from a trivial wave function. But now with G2 symmetry, we have another non-trivial SPT phase. And then if I apply gauging map, then we get the ground state of the doubled semyon model.
I guess I'm trying to distinguish what you're doing here from the gauging map that you had in the previous slide. Is this?
Oh, it's different.
Yes. So I'm trying to understand what the difference is.
Oh, I see.
I mean, obviously this group.
So this U is a unitary transformation among this H0 space. So gauging map goes from H0 to H1. This map goes from H0 to H0. Yes. Sorry, this slide has a very horrible typos. So I wanted to go to the next. Anyway, so by using this quantum gate, you can construct SPT wave functions. So since SPT wave functions are symmetric, so we can apply the gauging map, and that is the key idea. So you first start from trivial state. That corresponds to a ground state of the quantum double model. But now, since SPT wave function is symmetric, so I can replace these spins with one-dimensional SPT wave function. So I just remove these spins and then put SPT wave function. Then the entire system is still globally symmetric. If I apply spin flips everywhere, still this is invariant. So I can apply the gauging map. But it turns out that this gauging map is exactly same as creating a gap domain wall here. The reason is in this region, the system still is invariant, but only I need to modify things only around this blue region. So I'm creating a gap domain wall. And it turns out by studying the cocycle function, in this case, two cocycle function, I can always know how my anionic excitation transform upon crossing this gap domain wall. Now the idea is very simple. I just want to move and sweep this domain wall over the whole entire system by enlarging it. If I can do that, then by doing this, I'm changing the types of anions. So this is definitely a logical gate. And the corresponding operation in the original system is I just make this 1D SPT wave function bigger and bigger and then sweep all over the system. But the point is this operation of making SPT phases bigger and bigger, I can do it by using local symmetry protected unitary. And it turns out there exists a low depth quantum circuit which make this domain will propagate all over the lattice. So by using this argument, you can actually construct a logical gate. And I would like to, I need to do a lot of complicated calculation, but I can verify the action of this logical gate. So in d-dimensional quantum double model, you can span the ground state as follows, and you can list all the Pauli logical operators. So this X is a co-dimension one logical operator, and this is one-dimensional logical operator. Then you can compute a group commutator, and this is defined like A dagger, B dagger, AB. Then, so this is the logical gate I constructed from d-cocycle function. This basically corresponds to sweeping d minus one dimensional SPT wave function. Then I need to think about this sequential group commutator. And then by taking it d times, I will eventually get some phase. And this phase is given by the so-called slant product. And I didn't explain the slant product because it's a bit complicated, but such a thing exists. And if this value is not equals to 1, then you see that this operator belongs to this level of the Clifford hierarchy, and it's outside of the d minus 1 level. So you have the action which looks like this. So this is the reason why I can construct this level Clifford gate easily. Okay, so yes.
Can you go back to the last slide, please?
Yes.
What do you mean by the Pauli logical operators? When the group is not like D?
So I'm thinking about quantum double model with abelian symmetry. So this Pauli means just generalized Pauli. Okay, so I would like to make some comments. So far I'm giving you a very generic framework, so probably you wonder what's the relation to topological color code. So we already know that topological color code has transversal RD phase gate, which belongs to the this level. So this is a long known. This has been long known, but recently we proved that this d-dimensional color code is equivalent just to d copies of the toric code, d-dimensional toric code. So you just need to put d copies of toric code, and this is as good as the topological color code. This means that d-dimensional quantum double model with Z2 to D is the topological color code. Now for this symmetry group, we have this non-trivial d-cocycle function. And this has a non-trivial sequence of slant product, and therefore I can construct a non-trivial logical gate. And it turns out it is a d-qubit control Z gate, which means I use this. So this is a 3-qubit control Z gate. So I'm using this qubit as a control, and then this is a target, and you apply phase. But you know that this gate is symmetric on the XYZ, so it really looks like this. And this gate belongs to the this level. And if you apply this RD gate on a torus, on color code on a torus, then it's actually this gate. So this is nice. Okay, so then I finally want to make a few comments on condensed matter theoretical implications. As I said, I can construct a very weird domain wall. So this is the color code. I didn't explain the color code, but such a thing exists, as you know. Then R3 gate is transversal, so I can apply it only on the right-hand side of the system to create gapped domain wall. And this gapped domain wall is very weird. Now, as you know, in the color code, you have point-like charge and loop-like flux. Now, you send this loop-like flux, then this loop-like flux must change into some object, which is composite of loop-like flux and superposition of electric charges. So remember that electric charges are point-like, but they form some line-like object. But they are superpositions, they are not eigenstate. And this is actually a locally unbreakable loop in a sense that in order to create this loop, you need to apply some unitary, local unitary on a disk. So you cannot eliminate it locally by doing something along this loop. So this is some well-defined geometric meaning. So this is kind of weird because this basically implies that in order to classify gapped boundaries and gapped domain wall, you really need to think about this weird object of superposition of electric charges. And so this is not like a random superposition of electric charges. Actually, it is related to 1D G2 cross T2 SPT phase. So if you measure the total number of electric charges, it's always even. And why this is interesting is because recently Michael Levin and Chen Ji-Wan proposed that in order to fully understand the 3D topological order, we need to think about three-loop braiding statistics. So that's defined as follows. You have three loops, and then you first braid alpha and beta in the presence of gamma. Then by doing this, if you are lucky, sometimes you get some non-trivial statistical angle. So I just computed this superposition of electric charge and three-loop braiding for this superposition, flux and flux. And I indeed get some -1 phase. So in the color code supports this non-trivial three-loop braiding. Well, I said color code, but it's just 3 copies of the toric code in reality. And this argument actually holds for any quantum double model with abelian group, and this statistical angle can be again computed by taking slant products sequentially. In fact, this three-loop braiding is like taking group commutator twice sequentially. So all these observation implies that we definitely need to generalize the notion of Lagrangian subgroup. Of course, it needs to include superposition of anyons, and also it needs to consider triviality of three-loop braiding and so on. Okay, so here is the summary of the result. So, so the original motivation was, yeah.
If you can go back one slide. The superposition of anyons must be fundamentally different from usual anyons in the sense that anyons have characteristics that it cannot be destroyed or...
sorry?
Anyons, by definition, cannot be destroyed by any quantum operation, whereas superposition can be easily destroyed by just projection. So what's the significance of the superposition of anyons?
So actually, so that's a good question. So the way I view this superposition excitation is actually as a defect line. So right now I'm sort of applying unitary transformation to the wave functions, but I would like to actually think about this as a transformation to the Hamiltonian. Then you can actually view this superposition as a defect line, which is like a well-defined object in the Hamiltonian. So you are modifying the Hamiltonian term. And this line, the defect line acts like a, so defect line acts like a smaller domain wall. So if you actually send the magnetic flux so that it intersects with this superposition of anyons or as a defect line, then you actually need to pick up a pair of electric charges. So it's like a smaller version of the domain wall, but in smaller dimensions. Yeah. Anyway, so here's a summary of the result. So yes, so we wanted to find transversal logical gates. Well, I'm relaxing the condition. It's a low-depth quantum circuit, but somehow we can construct such gates by using group cohomology or the theory of SPT phases. And so far I have been talking about ordinary SPT phase with global symmetry, meaning that symmetry acts everywhere. But recently we have people have been finding that SPT phases can be defined by using more generalized global symmetry, where this symmetry operator acts on codimension 1 or codimension 2 surfaces. So that's called like a higher form SPT phases. And in another paper, I also found that such SPT phase also often leads to logical gates in some interesting way. So these connections are probably very interesting to look at further. And also this studies of gapped boundaries. 2D, it's almost done, but 3D, nothing is known. So it's probably a very interesting future problem, and it's nice because by studying these things, these things are closely related to each other. So anyway, so thank you very much.
Time for questions, if anyone has any. I know that there were a lot, of course, during the talk. I guess my main question, so in a very practical sense, does this give a reasonable method for generating kind of idealized transversal-oriented gates in 3 dimensions that we can maybe even implement?
So, yes, that's a good question. So right now people are trying to construct transversal logical gates because it's easier to implement instead of like low-depth quantum circuit. But for example, in the topological color code, the construction I know, so if you try to increase the dimension, maybe you can embed everything in. So let's increase the dimension. Then the support of the operator, the number of support, grows exponentially in the construction I know, at least. But if you use just toric code, then it's not exponentially growing. But the price I need to pay is this transversal gate needs to be replaced by a finite depth circuit. So I don't know which is better. At some point, like measuring syndrome by using this exponentially big operator costs a lot. So I think it has a meaning to think about finite depth circuit still, if it's reasonably finite.
If there are no further questions right now, let's thank Beni again.